Hello. So, how's it going? So, let's start with who I am, first of all, although I've been already introduced a bit. So, I'm an associate professor in France. Formerly, I was here in Estonia, so I thought it was nice to come back the week of the summer. Yeah, I am a streaming enthusiast. So, I work with data in general, not just streams, also graphs. And you might know that, I don't have to explain what data are. How many of you have worked with a database? Ever? Okay, indeed. But you might know that data can be big, right? You might have heard the term big data, I guess. Like, very big. Like, sometimes they are so big that they never end. And that's what this talk would be about. Like, oh, come on. Yeah, enjoy it. So, how many of you have ever heard the term stream processing or data stream in general? Oh, quite a few. Nice. Nice. How many of you have heard it from me? Only one? Oh, okay. Hi, what's up? Cool. So, a stream is a special kind of data set, right? It's, as I said, it never ends, it's infinite. But it has some interesting features that can help us dig into it. It's ordered, typically by time, right? So for the sake of this talk, we're going to imagine to have a stream of colors, just, to keep it simple. Every square in our stream is a data point, time-stamped, and for time we use just, 1, 2, 3, 4, 5, and go on. So we have many points coming to us in order, right? So an element in the stream is called an event. I promise you this won't be a lecture, I promise you. Just to get some context together, right? And an event has usually a payload, which means it contains some information we are interested to get. The problem arises when we want to analyze these events to make sense of them to power our analytics. Now, I was thinking to meet a crowd that didn't know what stream processing was. So I wonder if you can imagine the size of the problem, right? And since 2018, the amount of data that is produced as a stream is growing every year, hugely. By the time of 2023, so next year, we expect 1.3 billion of IoT devices deployed just in Europe, okay? So the number is insane, and this is touching the tip of the iceberg. We can have streams from social media, stream from any sort of application which tries to operate in real time. And like my favorite here is the 3.4 million of snaps per sec per minute, which I don't know what people are actually sharing, but maybe you can enlighten me on this. But the problem is not new. So the problem is timely. It's a problem today, but the problem is old, as many problems in computer science. There always exists a bored scientist somewhere in the 80s that thinks, what if we could do that? And like an updated timeline of what stream processing is this one. I might have forgot something, so I'm striving for precision. Okay, so those that are here are seminal works. Maybe I missed something, but everything starts with this work from Michael Stonebreaker. Again, in MIT, no wonder, they start thinking about how can we process the data stream? How can we make sense of them? What are the requirements that can lead us to build application that actually makes sense? Now, if you want to read the paper, I encourage you, but I'm more of a visual person. So to pitch this, usually, usually I like, to associate things with faces. That's about the Hateful Eight, okay? And we're not gonna need all of them for today. We're just gonna need two, which might raise your attention on what are the current industrial needs. So the first one is query with SQL. How many of you have wrote an SQL query? I expect at least those who said you use a database. Pardon? We just looked at the table. You just look at the table, like you scan them. You're a MongoDB person. That's what they do there. And the second one is here, the last one, but the notorious one, which is respond rapidly and instantaneously. Because speed matters here, right? Why? Because the data are changing so fast that if I wait too long to process them, they are no longer valuable. They don't mean anything anymore, right? I want to know now what is the fastest route that will drive me to the bar, right? Actually, if you know. Not in 10 minutes. In 10 minutes, I already changed my mind, right? So Stonebreaker and his team in MIT list down this requirement. It's 2004, okay? So long time ago. Things go on a bit, and 2005, in Stanford this time, so another Ivy League university, a woman with their team, Jennifer Widom, which she will appear many times in the history of stream processing, okay? Like the Stephen Hawking of stream processing. She designed a new paradigm, a language that allows us to do computations over this infinite data structure. Now, you are developers, right? Right? You're already sleeping? It's like 5 minutes. Okay, you are developers, right? Okay, so infinite computation sounds nasty, doesn't it? Right? I mean, I've been taught theoretical computer science, things tend not to terminate, right, when the input is infinite, and that's not nice. Like, we would like our program to end and give us results. So how do we do that, right? How can we process something infinite? Well, scientists are smart, but they're also like punts. So I say, well, maybe the processing of an infinite structure is an infinite answer. Like, duh, and what can I do with that? Well, a bunch of things you can, actually. So one thing you can do is stream computing. For example, in our beloved stream of colored boxes, we can sort them out, right? We can divide them by color, from a mixed stream of all the possible light spectrum, right? We can have a stream of blues, a stream of red. Okay, maybe you can mix them. But this is not quite enough, right? It's essentially filtering. It can help us clean the data. It can help us remove things we don't want from there, but doesn't help us doing any anomaly detection. It doesn't help us performing transaction in a stream of tickets in my online payment mechanism, right? It's too little. What we want is a stateful computation. We want to remember something and analyze it. As soon as the data change, update the answer. So this is called continuous querying, okay? And again, scientists, and they're funny. We are funny. Like, so what they do, well, let's say I have an infinite structure. I can't compute it all. So I can just maybe scope my computation, okay, and stick to that part. And then I have a partial answer. It's not the finite one, but maybe it's sufficiently relevant to perform my action. So they invented a novel concept, groundbreaking, the window, right? Yes. So they scope the computations to a finite portion of the stream, and they compute it there. So we can ask, how many red-colored boxes in the last minute? And as the minute changes, because new data arrive, I update the count. Simple, powerful. What I can do with this? I can do pretty much everything I can do with database now. I can do joins. I can do projection selection. I can do different kind of joins. I can potentially combine two infinite streams. So databases are not bad after all. If I have the full power of SQL in my hand, I can go the long way, right? Well, let's go back to, I don't know where to point this. Still didn't learn. Okay, let's go back to the timeline and a bit of digression. Okay, so SQL is awesome. Everybody uses it. It's the only language that lasts. As someone said, I think it was the PHP inventor, there are two kinds of languages. Those that get criticized and those nobody uses. SQL got a lot of criticism. It means it's very much used. But for some people, this is still not enough. We want to do artificial intelligence, right? I can mock them myself because I tried as well. So there are two moments in the history of stream processing where people trying to combine it with different form of artificial intelligence. First, it was deductive. It's still ongoing, actually. You might have heard rule-based system, expert systems. And this raised a bit the word of complex event processing. So you're trying to recognize patterns over the stream and act upon their detection, okay? Simple languages, regular, rule-based, essentially. If this, then that. Adds something to the stream, the SQL part. Yes, it's something I cannot do in SQL. And then give the programmers, the developers, a bit more flexibility when they need to react upon things. Second encounter with AI is more recent, 2009, 2010, and it is streaming machine learning. I don't know if you have ever heard of MOA, or Apache Samoa, which tries to do online learning on data streams, which is tricky because if you have any experience with machine learning, it kind of like looks like an iterative job, right? You need to loop through the data, but in streaming you can't because the data are going to expire. So how can I learn fast without seeing the data twice? It's a problem. So there's still research on this. Just to tell you that I won't go over SQL today to give you the hint, but there are many branches of this topic, and they're all interesting, at least for me. But the event that I want to focus on is this one, which is 2014, and is the event of big stream processing. So Tyler Akidau from Google wrote this paper, which is called a data flow model. Essentially, something changes in the context of big data. Streams are infinite. They are, they never end, but they can also contain a lot of data per second. So I need to scale out. When I move from a centralized database to a distributed database, things get nasty. Transaction get nasty. One thing gets particularly nasty. The order is not reliable anymore. So the nice property of the stream, the time order that we love it and let us do the windowing and scope the computation, aren't reliable anymore. Because the distributed nature of the system makes data out of order. I have delays, I have network latency. So Akidau and his team at Google studied the problem of reconciling these two things without sacrificing too much latency. It's a very low-level system perspective, okay? But it impacts the correctness of your application to a point that you cannot really use it. So you need to choose, do I compute little data, or if I want to go big, I need to scale. And then another event happens in the big stream processing work. Apache Kafka. How many of you know the book I Love Logs from J. Krebs? One, two, a few people. Nice. How many of you know Kafka? Ooh, like, nice. They don't pay me, so just to know. So what happens with Kafka? That the timeline branches, right? So I'm a super fan of Back to the Future. So what happens is that from continuous query, we deviate to streaming system. And this might recall you something called microservices, okay? So Kafka gives us the perk to endorse the distribution even more, okay? I don't care anymore about the distribution. Actually, that's an advantage. I decouple my application as much as I can, fragmenting them to the point that I get these dead start-like graphs of interconnected services. Why this is a good idea? Because now I can build streaming systems. I have a fault-tolerant, strong, persisted log that powers any application, and then using a stream processor that computes the windows, I can build views and create an unbounded DB that can work on any data in the distributed fashion, because the log takes care of reconciling the truth, because logs don't lie, right? Try to imagine this is a philosophy you already know. How many Linux users? How many Mac users? It counts as well. I'm a Mac user too, so it's more or less like this. So you have your terminal, you do like echo something like digit is awesome, and you pipe with one of my favorite program in the Linux terminal, Kausei. That's what I use to greet my students in class usually. And then you have a brand new software that is composed by two softwares, Echo, I don't know how to pronounce it, sorry, and Kausei. So I can do things like, I use for the demo, it doesn't work. I can do microservice 1, pipe microservice 2, pipe microservice 3, and this is called the Unix philosophy of distributed data. So the Kafka component acts as the pipe, right? Because the log contains all the events, everything that happened so far, and let me reconstruct the state, or how we say in France, l'état c'est moi. Right? I don't know if you get the reference. It was a bit too much, but I have to endorse my French employers. If you don't know Kafka, most of you do know, just a conceptual view of it. You have 4 components. Producers and consumers, respectively, write and read to the topic, which organize logically the messages. Messages are just key value pairs, like in the color example. You can put pretty much whatever in a message, as long as you keep it small, less than a megabyte, even smaller. Why? Because the message is a unit of computation. The smaller you get, the faster you go. Kafka doesn't know anything about your data. It doesn't process them, okay? So your unbounded DB, here, it's just a matter to organize the data logically over time, okay? As they arrive, though. It is the view that contains that should be constructed according to your application needs to build the analytical perspective on top of it, okay? So if you need to analyze the data, you still have work to do. It's not over. That's why the Kafka people invented the dual streaming model, which is a model that tries to combine the sophistication of SQL for the analytic part and the system perspective that was introduced by Google without sacrificing too much simplicity. 2 abstractions, streams and tables, changelog of the table. It's very abstract, I know, but the best example I can tell you is you're playing chess. On one side, you have all the moves you do, okay? On the other side, you have the board in a specific moment in time, okay? The dual streaming model lets you move from this, like a stream where you have a location of a person, to the count of how many locations a person visits. And seamlessly, you can move from this back to the streaming world, where you have like the changelog of the stateful table that contains your aggregation. You're practical people, I know. So I didn't show you any code so far. I'm sorry, academics. But it exists. There is some Java code for doing this. Yeah, I know it's Java, big data. You can use Rust if you want. There are many libraries for that. So you have all the power of functional programming to do the stateful part of your computation, all of it. So flat maps. And this will take care of the stream computing part. You have to implement your own joins, back up by a window mechanism to construct your aggregation. And the API of Kafka Streams, which is this library Confluent built on top of Kafka to guide you through the continuous query process, allows you to use the same system that you're using to glue together different microservices to perform the analytics. Sounds like a good deal to me. Again, they don't pay me, just to clarify. So, in summary, because I have less than a minute, the dual streaming model simplifies the way we can reason about time and the unboundedness of the data. But we still need the infinite memory, though. So Kafka doesn't solve the problem that the stream is infinite. You need to choose the right window, which is convenient for your business problem, right? That's unfortunate. Retention is very important, though, because the stream now is backed up by a fault-tolerant structure, like the topic, Kafka topic, and you can keep the data there as long as you want, or as long as you're willing to pay. The idea here is that a topic is a very low-level abstraction, like the Kafka topic knows nothing about the data. You raise the level a bit by adding a schema, and you go to the final analytical spectrum where you have the table like in a normal database by performing an aggregation. just a bit of reference, and I conclude saying that we saw briefly a query language perspective for stream processing, inspired by SQL, a system perspective of stream processing that tries to solve the problem of out of order when you go distributed and you are to deal with network latencies in order to process very big streams. And at the end, I presented you a hybrid New Hope, which is like something in between that is sufficiently simple to be understood by a programmer which has no experience in streaming internals, let's say, but does not neglect the expressiveness of continuous computation, which are necessary to act on time. Here are the pointers. Thank you.
I promised you that I don't know if you, I promised you that I'm not coming to the stage, but I see there's so many new people. So for a second, let's all scan this code so we can ask questions from the speakers. You can post your questions during the whole day. During the whole speech, but the same code for the whole day. As well as you can rate the speakers there. So you can leave your comments and everything nice you have to say.
Or nasty.
Don't write nasty stuff. Scan the code and word back to you.
Okay. But it's question time or like, okay. No, just the panel? Okay.
Yeah.
Right. All right, so since you didn't have enough of me, the next step is I'm going to invite two people who knows a lot about this because they have been using this in production to talk about it with me in a panel. Of course, your question is also welcome, not just mine. So first, I'm going to invite Mario Pauskar, which is a CTO at Ridango, and Rivo Heinsalu, which is a software engineer at Katana, to join me on stage for a panel. So let's welcome him. Hi.
You're my #1 fan.
Hey. So you brought your
fan club.
Fan club. Yes, nice. Okay. This is very uncomfortable with the mic. Okay, so first of all, thank you for joining us. And let me just briefly discuss a bit the use cases. I'll start with Mario. So at Ridango, you do real-time processing for the payments, and you have strict latency constraints. Can you tell us a bit more the real-time requirements of your use case?
Yeah, for example, where we really started with Kafka and stream processing was actually related with data what we need to provide for public transport, getting better traffic lights from traffic control systems. And there is latency very crucial, so that the time from bus, where bus is located, and reaching data to the third-party system around less than 1 second, moving over the 3G and so on. So this is where we started.
So quite fast,
Yeah.
indeed. And moving to you, Rivo, Katana deals with manufacturing, so as well is being praised to simplify the software part for manufacturers. So can you tell us the requirement in real time for your the real-time requirements of your use case?
Yeah, there are two things probably that I'm gonna highlight. Both go around inventory. So I don't know how many actually know what Katana is or does. We are cloud-based manufacturing ERP software, providing our customers visibility and workflows to manage their incoming and outgoing sales orders, manufacturing process, inventory, and everything else. So for us, in the real-timeness, the key element is inventory. And for many of our customers, what Katana is also for them is a central place for or source of truth for the inventory. And for the customers that have many different sales channels, they need a central place as a truth. So if anything happens or like any of the inventory levels change in Katana, it means that we have to be able to communicate these back to customer different inventory systems as well, either via integrations, public API webhooks, and so on. And another thing that's very unique for Katana and probably separates us from all or most of our competitors. That's called something real-time master planner. So this is the main tool for manufacturing planner. And when they, so in essence, it's a order availability and priority matchmaker. So once the manufacturing planner actually, what they use it for is that they have to be able to see real-time changes when they change priorities on the production lines. They have to see if they are able to continuously process and manufacture everything without stopping. So every time the priorities change, we run huge calculations and we have to provide this feedback near real time in order for them to make quality decisions.
Okay, thank you. So back to you, Mario. Since we discussed before, we presented the history of stream processing, and the question comes naturally: when you decide to move towards this kind of platforms, when these requirements start, show up?
It was around a year ago when we started with that specifically. And now what we have discovered that Kafka and stream processing has so much more capabilities and things what it can provide for us. So it helping also putting monoliths and old legacy applications and link them together very easily with the new modern microservices approach. So from there we have started to use it more and more, and it's like a little bit snowball effect. When you going into there, then you can't get out anymore.
So your developers, elaborating this, your developers seem happy of the transition?
Actually, all of these who already hooked into it,
okay,
they are more like sponsors for the system and going to commercialize internally it more and more, that they use it here or use it there. So of course, all people yet haven't touched it, but more and more are getting used to it.
Okay. So actually, we have a question from the audience, which I will address after asking you the same question. Indeed, when this transition started and when these requirements start showing up.
Yeah, I guess pretty much the same, a little less than a year ago. And the main reason for that is that why we started looking for another solutions than just the regular REST-to-REST communications or some other messaging queues was just that when first we started, we went to for very, very small customers and low amount of data. Mm-hmm. But now we are going after bigger and bigger customers and providing them more features that the bigger customers need. But at the same time, the amount of data also grows that much, and the domain dependencies and everything else. So that was the time when we needed to do something, and we decided to try out what we do. We have implemented change data capture, which in essence means that every change you make in the persistence layer is also mirrored to the Kafka topic. Okay. So basically you have a copy of all your data entities, latest states in the Kafka. And what this has helped us to do, I know many companies mostly use it for analytics purposes, pull data together from different services to data lakes. But what we actually also do, we have built application logic on top of it. So different domains are interested in certain changes in other domains. And previously it used to be that one service had to know a lot about another domain's knowledge. So what it means is like, I finished this, I need to now notify this and that. Okay. What now can happen is that I do my stuff. I don't care what happens after that. I just tell that I did this. And if you're interested, do something about it. So that's how we build application logic. Not everywhere yet, but we are moving more and more towards this. And another thing that we use it for is that, as I told, Katana creates great visibility over different views. So the planners can effectively see all the different data. Mm-hmm. But this also means that some views contain data from 5 or 6 different services. And we don't want to introduce this complexity and knowledge to these services that they need to do something. So what this helps us to do is that we can now combine and aggregate data over many services, enrich it, and for example sync it to Elastic, so each team can independently build complex search models on top of that.
So your interaction pattern remains through search at this point as well. Okay, interesting. Elaborating on your answer, actually, it seems to me that the use case emerged internally, while in your case it was more pushed by some of the existing customer. Is that correct?
We had actually as well one customer,
Okay.
and we provided this traffic information for a traffic priority system. Okay. But this timing, what we were able to or capable of doing beforehand, was like around up to 5 seconds, and then we tuned it and got it to the 3 seconds latency, and it wasn't good enough. Because if you imagine that the bus is driving and traffic lights need to prolong the green wave or start sooner green wave for the public transport, if you this timing is off, then doing all of that too late. So then we got actually a big push from a customer who really wanted it in Sweden, and then we. Tested out different solutions, and this is how we reached to the Kafka.
Okay, actually there is an interesting question from the audience also for you, which is how are you affected by on the latency point of view by external systems? How can you guarantee this lower than 1 second latency if you are integrating external systems? If you do it, maybe you don't necessarily.
We are using it's like GTFS push, okay. Like standard, which is used in public transport for this real-time data exchanging, and this is the service what we're using. So we are pushing the data, and yeah, we have in contact with this other company, and we know that it's working, but our side ends where we are pushing out this data.
Okay, thank you. The second question also comes from the audience. I think it's interesting is that for both of you, like when does the log becomes the bottleneck? When Kafka is actually, do you experience any situation where Kafka or any other alternative like Pulsar, for example, is actually the bottleneck, or in general is situated somewhere else in the application?
I would say, like for our cases, it's usually somewhere else. How fast can you process, and how rapidly can you grow the concurrency? So this is what makes it a little bit like a bit learning curve there, that how to concurrently process the data in the Kafka, like what it depends on. Yeah, so I guess this is the thing, and if you can provide as many as consumers you want, and you can do parallel processing, I think then, yeah, for us at least, there hasn't been a bottleneck in Kafka, because our data amount is not that high for that problem.
Okay, and for you?
Kafka itself hasn't been bottleneck for us at all, but what we, if you're talking about learning curve, at the beginning when we started to push this 1 second data from very many data sources, as there is more data than only this GPS location, there is a lot of data about what bus condition and so on. So what it turned out at the beginning, we had retention 30 days, and it turned out very fast data amounts were growing more exponentially than we were planning to, and this was something what we needed to do, and also what some at the beginning to get it working for production. There were much more possibilities to configure it one or another way than we expected at the beginning. At the beginning, it was just like put it work and start using, but actually it's much more complex system. So yeah.
I mean, the tendency with stream processing is really like throwing everything inside the queue, but garbage in, garbage out. Indeed, like in any data system.
Yeah. Basically, yeah. As more you put in, the more CPU and memory you need to put. But this is like simple part. We actually at least haven't seen any bottlenecks there.
Okay.
On that part.
Another question from our audience, which is very active, Davi, I would say. Like how long you leave the data in Kafka or in the queue in general? Like what's the retention policy you keep?
It depends, but this concrete data, what I was talking about, we realized that we don't need this data there more than 2 days. But okay. Of course, we are storing it to the database for longer usage.
Okay. Same for you?
Yeah, so question. For us, there are 2 types of things we do. We actually use it from service to service communication as well. Mm-hmm. And then this depends on the nature of the topic. Like, do we want to retry until something fails, or we just try, and if it fails, it's fine. So for such things, 1 day is enough. For the things that we actually, if we run to issues, we keep retrying until we actually fix the issue. So for these, we keep 7 days in order to actually being able to have enough time to fix something. And for the CDC topics, we are using actually log compaction, which in essence means that the latest state of every row in the database is kept in the Kafka topic forever.
Yeah, this is something I didn't have time to explain in my presentation. I would love to, because it's an interesting part of the duality model of Kafka streams, actually, which brings nicely to the next question I have for you guys, which is about streaming pipelines. I mean, so far we have spoke about Kafka as a system integration mechanism. What about analytics? Do you do anything yet? Mario, first.
Yeah, we were considering, but we saw that these use cases what we currently have, we don't need how to say deep needs from Kafka itself. We can handle it much more easily with our external services. So we're using it more like producer and consumers way, and doing all of these calculations in Java code, as our main backend stack is Java, and it's easier. We already know it. We know how to use it. To do it inside Kafka with Kafka streams, you need to learn new syntax and so on. So, but I can't say that we are not getting there if these use cases get more demanding. And as I said, it's a little bit like a mind-blowing thing that you're starting from somewhere, starting to scratch the surface, and at the beginning you have some use cases on your mind where you're starting, but actually this area is developing very fast, and gives more and more possibilities what you can achieve and do with the platform. Okay. So it can happen. Don't know yet.
Yeah, I mean, we have plenty of ideas where it could be useful to use the stream processing, but why we haven't implemented any of it, it actually comes down to complexities and the nature of the topics. So one thing we could, for example, do, we will now have new product team, which is for reporting. So in essence, they will start providing customers real-time information, for example, cost of goods sold in this month and so on. And what the stream processing could help us to do is, right now you have 2 ways to do it. Introduce it in the code level, that every time something happens, that changes the cost. You notify something and you recalculate and cache the value. And another option would be to do the same thing without any introduction to code, knowing about this, would be pull into this stream for the topic that you're interested. And on the live stream, you calculate, like sum it up all the time. Once there's a break, you keep it in the KSQL database. Once another entry comes in with the same update to the same topic, you will submit another one, and that will take out pressure from the application and the knowledge. So these are very great examples what you could achieve, especially in reporting and everything like this, and even inventory calculations. But the problem for us would be then to actually trust this value. We couldn't use log compaction. We would actually need a full history of every single event, and it's just like something that we haven't yet taught how to store these events forever. So it goes to something like event sourcing area already. So
yeah, you need to design well the events you captured in order to scale better at the end of the day. Like event sourcing, for those of you who might wonder, is like a subset of domain modeling, a technique for data warehousing that focuses on the modeling of the events, the component of the stream in our color example. Which actually this relates well with the question from the audience again. I will answer the one on the payroll of Confluent, don't worry, because they keep upvoting it. The question is if you have any like scalability stories to share, like a situation where memory issues, things where memory issues, elasticity problems, things like that, where streaming was an obstacle rather than support. I mean, these technologies are in their infancies at the end. So, do you have any example in that sense?
Where it was obstacle?
Yeah, when you have scalability situation
Yeah.
where the architecture didn't scale well, so you need to manually intervene and fix something because of the new streaming architecture.
I think one thing for us was actually learning and understanding all the complex configurations. Like when you start like building your consumers using default configurations, then you actually have to understand what they all actually mean. Like how does the session timeout and heartbeat interval work together? Like if you don't make it on the time, everything keeps endlessly repeating, and eventually you have only one consumer left, and that's also overloaded, for example, and you keep repeating the same events. Another thing is like if you pull into as a new consumer to existing topic, what we had noticed that when for example, we are written everything in Node.js, which has eventual garbage collector. So when we pulled initially to the new consumers into the topics that are already filled with gigabytes of data, we started processing it so rapidly that we just overloaded the memory because garbage collector couldn't have yet time to clean it up. So, so that sense, yes, it needed tuning, and it all comes down to basically knowing your configurations and how to handle this.
You have a similar experience or completely different but related?
We have had more with the disk, as I said, the capacity-wise, that how much data you're writing. There were some things related to how you partition or how to compacting the data there, how big chunks you are storing. There were big difference for us. But from memory-wise, yeah, I don't remember any bigger issues. Maybe when we were starting it up at that time, but then it didn't come to my attention.
Okay. So that brings us to the next point in my list of questions for you, which is more advanced analysis and query paradigm. We agreed that you don't do that yet, but we've been chit-chatting before on the possibility. Especially at Ridango, you have strong consistency needs. Like we want the payment to be effective. So how do you think streaming positions towards that? You're happy with the current offer? You're not?
Yeah, basically all who are from banking know that transactions are very important, and you can't lose customer money, or when you happening some sort of split brain and you have like here one money and there another money, then you could imagine what will happen next when you don't know what is correct money. So we're a little bit similar. We're ticketing data, what we're storing, and if people are purchasing tickets or when they are peeping and validator, then everything needs to be correct and in correct order. So transactions are from that sense, at least so far, has been very important part of our ecosystem. We are using transactional producers for some use cases right now. Okay. With Kafka, with some data, what needs to be precision, but we are not trusting it so much yet to put very big and most important use cases top of it. So we'll see how does it then evolve.
Okay, let me just comment. A transactional producer, since we discussed, I presented a bit the abstraction, is a producer that guarantees a certain order in the message sense.
It's very cool from that sense that you can actually send data, like producer can produce data, consumers can already load it in, but it's like in idle state until you're sending commit. So from that sense that you can prepare the data, if data amounts are big, you can like continuously have data flow working and then sending small commit messages only, and then it's active, this data what you have sent.
Yeah, but doesn't that simply mean that you are just doing at least only once delivery instead of at least once?
This is only once delivery.
Okay.
Yeah. But it depends on use cases. Yeah, as our product range is very big, and some like where bus is located, it's not so important there. if one bus location goes off. But yeah, as I said, some sort of ticket and price and all of these related data, we need consistency.
Okay, but wouldn't just the idempotency keys and things like this solve it?
I don't know in so details.
Okay.
This part.
But I guess that won't be sufficient because the payments occur on multiple systems at the same time, right? So how do you reconcile the different events across different? Like I go to a bus, then another, then another. Idempotency will keep only the last one, right?
Yeah.
So
yeah, that's true.
The identity, that's again on event source, the identity of the messages is tricky in their use case to the extent I understood, because it depends on who pays.
All of that was taken or has been and is also right now taken care of SQL and like traditional way. But now when you introduce this streaming engine, then for some sort of the data, you need to guarantee same things there as well. So.
Yeah, my impression is being working on streaming SQL now for 10 years is that the syntax is the same, but the semantics of the language is not exactly. So it is like there are similarities, of course. The work I presented definitely goes towards that, but we are at the beginning. Stream processing become production ready, let's say, or at least to the attention of companies that want to deploy in production since 2014, when Google said we do this. When Google said we start doing this, companies decide, oh, maybe we should that too. And but I have a question for you, Rivo, on the advanced topic on stream processing about like the need for additional abstractions. Like we discussed that you implement everything in your JS. How do you relate with the streaming libraries that they are currently available, Kafka Streams, for example, but any other? You mentioned already you use compaction topics, so maybe changelog streams. How do you position your current work in the realm of abstraction for stream processing?
Sorry, I actually don't get the question.
The question is...
it got so complex.
Yeah, I spoke for too long. Yeah, I distracted you. So the question is, in the current offer, you implement everything from scratch right now, as I understood. Everything is in-house. But there are emerging new libraries, aside from SQL, which is for a specific audience, let's say. On the developer side, how do you judge the existing abstractions for dealing with streaming data at programming level, let's say, since you implemented your own, as far as I understood?
Yeah, we did. I would definitely, or actually we are looking now moving probably and hopefully eventually to Confluent. So they would probably already provide us very up-to-date quality tooling that we don't actually have to manage ourselves. So just the sole purpose why we did and implemented some things ourselves from the scratch was just that we wanted something simpler. Like from day-to-day basis, we are still software engineers to provide features and send features out. So we don't actually want to manage anything ourselves. And at that moment, we didn't have a data team yet who would actually could manage and deal with everything and worry about fail-safe and everything else. So we created a very simple approach for that. But actually now we are seeing that this actually creates us blockers where we could actually already advance. And now we are looking for actually like professionals who have provided these tools already on the market, like Confluent.
Okay, which is a good answer, which smoothly go to the next topic, let's say, which is the human side of the problem, let's say. I guess, Mario, you can... we know you already have, now you have a data team dedicated. Do you have a data team dedicated for streaming at the moment?
No. Our developers are doing all of that.
Okay, and that's the second question which relates to this is how hard was to learn this for them? The learning curve was...
Yesterday tried to understand from our developers that who like started up all of that side, and at the beginning one guy said that it was very simple. Then I was, oh, really? and then it started to come up a little bit more. That at the beginning, like this first curve was like a little bit like what I said before, like mind blowing. That how you need to rethink a little bit how to think about data streams and things compared to traditional way. But if you get the first point, then each other has been seamless and easy, as we're not using today yet too many Kafka internal specific features. We're using it like as simple as possible, so that we're using it inside the Java, and from that sense, it has been a rather easy journey for us. And yeah, as I mentioned before, that everybody who touches it can't get hands off anymore.
That's a good. So you briefly touched this topic already, but more explicitly, how hard was it to install, like start streaming?
Well, I don't think the streaming itself was there anything very complex once you learned all the configurations and all the different setups and how this works together. Like we had a really simple approach there, but like I think the complexity relies somewhere else for engineers. It's the mind shift change. So from transactional, regular, or monoliths to actually what is the eventually consistent thing, like
the things you don't have anymore,
yeah,
like
so,
the storage.
So the mind shift changed from that, like I finished that, what now? Like who's gonna respond me? What's going to happen? So the mind shift changes, something complex. I think the most complex.
Okay, so I will conclude the panel before going to all the questions you asked, because I have a few to solve, but they are related. I try to sneak in those that were following the discussion with a hint to the future. Like would you be a 5-year evolution of your architecture, and what will be a 10-year evolution? So what you imagine? Can you stretch that far, or maybe like?
I think with 10 years, so many things
10 years
will
too much.
happen. When I was in university, then JavaScript was like some sort of plain bird. Who was using JavaScript? It was other different languages then. But now it's like main thing. If you don't know JavaScript, then you don't know how to write
web
exactly. So and it wasn't so long ago. So what happens within 10 years? Usually humans are very bad to interpret that. But in 5 years perspective, what I see, at least with our systems, is that to decouple systems, make it smaller, and think and going to the thinking where every system treats every other system as external system, which means that it's much more easier to integrate in the future with other providers. And we have had this need that at the beginning we're thinking it's internal, and at some point, we need to do integration, and then this pain to do this first integration takes time. But if you from the scratch up thinking that everything is external, then it's much easier. This is one thing.
You same question?
Yeah.
5 years, 10, I agree, is too much.
It's quite hard to answer that.
2.5, that's my last one.
Okay. So Katana is less than 5 years old, and we have shifted so many times already how we build and do things. Definitely we will either be fully or much more event-driven than before. But I don't know if I should throw in some fancy words like command query, responsibility segregation, and so on. So I don't know yet. Like
more adoption of streaming patterns. That's what I hope as well, that some best practice emerge, because at the moment it seems everybody is risks to reinvent the wheel, because it's not clear what is the best thing to do things, and that's what also we were trying to do at the university with the course we were preparing. So okay, let's move to the actual question from the audience. They are scattered across topics, so I will pinpoint a bit. The one with the most upvotes is quite technical. It asks, with the subscription-based model, which I suppose is the producer and consumer technique, PubSub, how do you assure that there are no loops generated by the reaction consumed by the messages? So I have an answer for it, but if you want to go, I'm not sure if it is related to your talk or mine, but it has I can answer it if you want. The answer is time. So the order it is guaranteed, and the consumer should be aware to not reprocess messages they already saw by keeping the current progress of time. That's why order is so important. I don't know if you want to add something, but
no. You can come to our box and talk there.
Second question is, this one I answer for last because I let them crave a bit more. How do you handle failures in network or in the application side, or even the broker side, like which relates to another question? Are you self-hosted or you take Kafka and everything you do from a cloud offer?
We are using the managed Kafka, yes.
You manage yourself?
No, we are using and paying for.
Same for you?
Yeah.
No, unfortunately, we need to provide also on-prem solutions. So of course, everything what's possible is in the cloud. But as we have needed some tenders, as our business works through tenders with public organizations, and some of them procuring things into their data centers. So we need to be able to put our setup working there. So there is no point to do different systems.
Mm-hmm.
So we're doing things per own. Yeah.
Okay. So
yeah, our take is basically like if somebody has done something very well, we just pay them money and use it.
Exactly. Someone has a problem. Like.
Sounds very logical.
Remember, the cloud is just someone else's computer.
Yeah, I can understand.
That was actually first thing when I joined with Ridango. That why doing it by yourself? But next answer was that we
have
extend the requirement.
I see. I think we have a couple of more minutes, so if you have more questions, please send them. This one we already answered. Okay, this one is actually, I think, for me, but also for you, I don't know. Since I'm not on the payroll of Confluent, and I'm sure I'm not, what are the alternatives to Kafka? Like I know Apache Pulsar, which is quite performant. I saw people using Redis with the same approach of Kafka streams. It's not exactly the same thing, so I will not recommend it because there are using a cache where you need a pub sub is not convenient. To my knowledge, Pulsar is the biggest competitor, and then you have of course Amazon Redshift, but that's we don't know what it is behind the APIs, so I don't know the internals, so I don't judge it.
But do they keep strict ordering?
I didn't check the last updates. I mean, I suppose they now do because you have to since Pulsar and Kafka did it, Amazon usually follows along. You have tried anything else before adopting Kafka internally, or?
Yeah, these things what you mentioned. We tried Redis. Pulsar we didn't try, but as we recently bought from Slovenia one company, they are doing Pulsar instead of Kafka.
Mm-hmm.
So both are good options actually.
I'll ask this question. Should I? They ask you why you're so cool. I sense it's come from them. It's anonymous though, but I have a feel. You want to answer the question?
I will let them to answer it later on.
Okay. Because okay. Fair enough. Okay, I think we have the last 30 seconds, which I will use for thank the guests. Thank you very much for this interesting discussion. Don't forget to stalk them at their stands. They will be there for answer even more questions. And thank you very much. Enjoy the rest of the conf.
Thank you.
Thank you.
Thank you.